All right, so we are starting chapter 5 today, and there are three sections in chapter 5 that we'll be going through. Let's put this on here. There we go. Had a little technical difficulty earlier, so things are a little out of the ordinary. So, our three sections are Newton's laws of motion, applying Newton's laws, and friction. So we have talked about kinematics, we've talked about force and velocity, we've talked about velocity and acceleration. So two of the most important quantities of physics are discussing force and acceleration. We've already learned about acceleration, that acceleration is the rate at which velocity changes with time. Force is a little bit of a new term um, that we're going to get into a lot in this chapter. And force is just a push or a pull. That's all it is. Two quantities characterize force. It is a vector quantity, so there's two things that characterize it. Its magnitude or its strength and its direction. So like I said, force is a vector quantity, which means we can represent it by an arrow, by its force and its direction, both. Okay. So objects that start or stop moving on their own are some of the things that we're going to be looking at, or that's what Newton's laws deal with. Objects that don't start or stop moving by themselves. And this observation was first made, or is the gist of Newton's first law. So Isaac Newton was the one who first discovered this observation that objects don't start moving by themselves and they don't stop moving by themselves. So here are the two key parts of Newton's first law. So you want to make sure that you have those written in. An object at rest stays at rest as long as no net force acts on it. And an object that's moving continues moving as long as nothing changes. As long as the object is moving with a constant velocity, it will continue to move with that same speed and in that same direction as long as there's no or other force acting on it. So if something's already moving, it will keep moving at the same speed and in the same direction, which means constant velocity, until another force acts on it. All right, so Newton's first law contains that phrase, no net force. So we need to understand what a net force is. So net force is just the sum of all the vectors of all the individual forces acting on that object. That's what a net force is. So for example, you sit down in a chair. There are two forces that are acting on you, the upward push of the chair and the downward pull of gravity. So gravity's pulling you down, but the chair is lifting you back up, and that's why you don't wind up in the floor. And so the two forces, the gravity down and the chair up, have to be equal. Again, otherwise you'd be in the floor or floating in the air. So the vector sum of the forces, or the net force acting on you in that case, is zero. Okay. So our experience tells us that an object, such as a box being pushed across the floor, will stop moving if you stop pushing on it. This occurs because of the force of friction between the box and the floor. What would happen if the force of friction was eliminated? Well, so if we think about, we have a box, and as long as we push it across the floor, it will keep moving. When we stop pushing it, then it stops moving. And the reason it stops moving is because the net force. So there's a force of friction acting here, and then there's your force. Well, if the force of friction is acting that direction, you are pushing in that direction. So If your force stops, so if we take away that force, then the friction is going to cause that box to stop moving, and it's just going to stay stationary. So if we eliminated the force of friction, then if we started pushing the box, it would just keep on moving, even without us continuing to push on it, because the net force would be, there wouldn't be another force of friction acting against it to counteract our force. So it would continue to move. So friction cannot be eliminated completely, but we can reduce it. Okay, so these are some examples of ways to reduce friction. So this is an air track. It provides a cushion of air so the cart rides on the air rather than on the surface. And so there's virtually no friction, because your friction comes from the contact of that object with another object. And that's what produces that friction. So if we can eliminate that contact, that direct contact, then we can greatly reduce the force of friction to essentially nothing. So once you push that cart, it's going to continue to move in the forward direction um, until something else acts on it. This time, it's not going to be friction acting on it. Friction is what acts on. If they were in direct contact, friction would act on it and cause it to slow down. But they're not, so it shouldn't. It will take longer for it to slow down. So, in place at rest on the level track, a cart will remain at rest until given a push. In accordance with Newton's first law, once the cart is in motion, it remains in motion until acted on by a net force. In theory, the track could be made infinitely long and perfectly frictionless. So the cart would just go on and on and on forever at a constant velocity. And this is what happens in outer space, pretty much. Things just, there's no air, there's no resistance, there's no friction. So you just float on and on and on and on forever, um, according to Newton's first law. Sometimes we refer to Newton's first law as a law of inertia. Um, Inertia is just the tendency of an object to resist any changes. The tendency of an object to resist any changes in its motion, that's what we call inertia. So if it's already moving, it's going to keep moving. If it's not moving, it's going to stay not moving unless another force acts on it. Newton's second law tells us how force can change an object's motion. So Newton's first law looks at the fact that an object in motion will continue in motion until another force acts on it. Well, Newton's second law tells us how that force winds up changing the motion. So throwing a baseball requires less force than pushing a car and giving it the same speed as the baseball. Why is that? Why is it easier to throw a baseball at a certain number of miles per hour than it is to push a car at the same miles per hour? Okay, well, the main reason is the car has a lot more mass compared to the baseball. Okay. So, an object's mass is the amount of matter that it takes up, and we always measure mass in kilograms. So, we need to remember that MKS system we talked about earlier on: mass, kilograms, and seconds. So, units of mass are always in kilograms, and then this table gives you just some example masses of different things. Okay. So, how does an object's acceleration depend on the force? So, if we look at the experiment below, the following figure shows that the acceleration is doubled when the force acting on the cart of the air track is doubled. So, this is our spring scale, and it's measuring our force. So our mass is constant, it's the same mass. If we double the force, 2F versus F, then we also wind up making it go twice as fast. So our object's force is determined by its mass, the amount of matter it takes up, and by its acceleration. So how does the object's acceleration depend on its mass? So now let's try changing the mass of the object and see what happens to the force. So this experiment illustrated below shows the acceleration is halved when the force acting on the car is doubled. Okay, so when the mass is doubled, actually, that should have been what that said. So when we double the mass, our acceleration is cut in half, assuming that our force stays the same. So that should be mass, not force. Okay, so again, the force of an object is determined by the object's mass and by the object's acceleration. They're both related. Which means this is our equation for Newton's second law, that the force is equal to the mass times the acceleration. And all we did with that is we just rearranged force acceleration to show that acceleration is directly proportional to the force and inversely proportional to the mass. So make sure that you write that down. Acceleration is directly proportional to the force and inversely proportional to the mass. And that is the mathematical expression or equation for Newton's second law. Rearranging the equation, we wind up with F equals ma. So force is equal to mass times acceleration is Newton's second law. The unit of force, obviously, is a Newton. Unit of force is a Newton, which is basically a kilogram meter, not basically, it is a kilogram meter per second squared. So a Newton is a kilogram because that's our mass. Meter per second squared is our acceleration unit. So a Newton is a kilogram meter per second squared. Okay, so make sure you know that unit is equal to those units. And there are some typical Newton forces. And here's an example of using that. An 1,800 kilogram car has an acceleration of 3.8 meters per second squared. How much force is acting on the car? You're just going to multiply those two numbers together. 1,800 times 3.8 is 6,800 newtons. The second law also applies to situations where you have more than one force acting on the object. So remember, when we started, we said net force is equal to the sum of all the forces acting on the object. Same thing here. When more than one force acts on an object, the force in the equation F equals ma is the sum of all of those forces acting on that object. Okay, so let's look at the next slide. All right, so here is another example problem. So Mo, Larry, and Curly push a 752 kilogram boat that floats next to a dock. They each exert a force of 80.5 newtons parallel to the dock. What is the boat's acceleration if they all push in the same direction? What's the boat's acceleration if Larry and Curly push in the opposite direction from Mo? All right, so again, like we've done in the previous chapter, since this is a vector quantity, we want to sketch out what's going on. So in the first situation, here is our boat, here is Mo, Larry, and Curly. They are all pushing in the same direction. So to find the force on the boat, which is then what we're going to need to find the acceleration of the boat, because we know the boat's mass, and we know Larry, Moe, and Curly each push with a force of 80.5 newtons. We can easily use that equation F equals ma to find the boat's acceleration. But we need to remember that that force has to be the net force, which is the sum of all the forces acting on it. So we're going to take notice that we have chosen the positive x direction to be to the right and the negative. So in the first one, they're all three pushing to the right. All three forces have a positive x component. In part B, Larry and Moe are pushing in, Curly and Moe are pushing in one direction. No, let's look at this a little carefully. There we go. Larry and Curly are pushing in the opposite direction of Moe. So the net force on that is actually going to be subtracting those out. So the Larry and Curly would be pushing in the opposite direction with a negative 80.5 newtons of force, and Moe would be pushing in the positive direction, which would be a positive 80.5 newtons. Okay, so we're going to use that as our equation. So we're going to take the sum of those three, and that's going to equal its mass times its acceleration. So this one is going to be 80.5 plus 80.5 plus 80.5. Whereas in this one, it was going to be 80.5 minus 80.5 minus 80.5. So the force is actually going to be a negative number, and then that's going to be equal to the mass times the acceleration. Okay, so we can see that worked out here, that we add all three together. And so they went ahead and solved for acceleration first with the general formula. And that is going to be equal to the sum of all three forces divided by the mass. So we're going to add all three together for A and divide by 752, which gives your acceleration of 0.321 meters per second squared. And it's moving to the right because the positive x direction is to the right. On the other one, again, they're going to rearrange and solve for ax first. And then it's going to be 80.5 minus 80.5 minus 80.5, because Larry and Curly are going in the opposite direction. And then we're going to, again, divide that by mass. So we're going to get a negative answer for our acceleration. And that's perfectly fine, because that negative sign tells us the direction we're going in. The negative sign tells us we're going back to the left. We're not moving to the right in the positive x direction, moving back to the left in the negative x direction. Okay? All right. All right, so according to Newton's third law, so the first law is basically that an object in motion will stay in motion, an object at rest will stay at rest. The second law is that the force on an object is equal to its mass times its acceleration. Newton's third law says that all forces come in pairs. There is no isolated force in the universe. If you have one force acting on something, then there's another force acting on it in an equal and opposite direction. So those pairs are always equal in magnitude and opposite in direction. The forces in these pairs, this is important to remember and write down, is that each of those forces in the pair act on a different object. So if we think back to our chair, in our chair, gravity, the force of gravity is pushing on us, pushing us down. So that would be one pair. The other pair, the other force in that pair has to be acting in an equal and opposite direction. So if gravity is acting down, then that other force has got to act up, and they need to be acting on different objects. Well, gravity is acting on me. Okay, the force, the pair to that, the other force in that pair would be the force of the chair pushing up. Okay. All right. So third law, commonly abbreviated, so this is kind of our common phrase for the third law, is that for every action, there was an equal and opposite reaction. For every action, there is an equal and opposite reaction. Okay. All right, so there's some examples of Newton's third law. So we've got a person pushing on the refrigerator and the refrigerator pushing back on the person. So they're equal and opposite. If the refrigerator's not moving, they're equal and opposite in magnitude and direction. They also are acting on two different objects. One force is acting on the refrigerator, the other force is acting on the person. Okay, so here's another one. We have the shuttle, the space shuttle, and the Earth. So there's no force of gravity downward of the Earth on the shuttle, pulling it down. That's gravity. And then the shuttle is also exerting a force on the Earth. Okay, so remember that in the three examples, the action reaction forces act on different objects. And so they do not cancel each other out because they're not acting on the same object. All right, so this is the end of section 1. We're going to talk about section 2 in the next video. If you have any questions, make sure you bring them to class, and we'll be working on practice problems with these in class. Have a great day.